Okay, there's another 2 minutes left. Do you have any question? Please do ask. Okay, ladies and gentlemen, let me start. It seems today is rainy. Almost half of the class stuck in the rain. They cannot get home. What we would like to do here is we're trying to today find a way to calculate the heat transfer coefficient. If you look at here, we define Nusselt number. Nusselt number is mentioned is the ratio of convective heat transfer. Convective heat transfer to conductive heat transfer. It means H over K over X. K over X represent conduction, H represent convective. Therefore, Nusselt number is a number shows how important is convective heat transfer to conductive heat transfer. And if we be able to find a relation here that shows that Nusselt number, it means heat transfer coefficient, is a property of Prandtl number. Remember Prandtl number? It was referring to motion to the momentum to conductive, and Reynolds number. If you're able to find a way for a flow that we can calculate easily the Reynolds number, because if you know the velocity, we can calculate the Reynolds number. And Prandtl number is only depend on the characteristic of the fluid, for example, air or water or any other fluid. Therefore, we can easily find a way to calculate the heat transfer coefficient. This is the objective. To get to this equation, I have to go through a lot of mathematics. Please stay awake. I can give you 5 minutes to go and pick up, prepare your coffee, okay? Stay awake. The question here is to understand the physics of the problem, that how we can calculate this number, okay? It's a mathematics, just you have to be patient to see the step that we are going to follow. We did it for conduction. We found a control volume. We wrote a simple energy balance, and we were able to find a solution for that one, okay? The solution was simplified solution, or it was advanced solution that we showed in the graphical. Here we're dealing with a fluid. Fluid is moving, okay? The fluid is moving. Therefore, we have a motion of the fluid. Therefore, if you want or you don't want, we have to solve the momentum equation, okay? You have to calculate mass balance equation, okay? Therefore, we're dealing with the mass continuity equation, mass balance, momentum equations for the velocity, and energy balance equation for heat transfer coefficient, okay? Therefore, that's we are going to try. Therefore, that's the idea. I would like at the end of the lecture to show you how we got this one, okay? And it's not the question solving the differential equation. That's not the objective, but the procedure we're trying to find that way, okay? First, therefore, we are telling here, we would like the double equation. We mentioned last lecture that we have to consider, control volume here. Here is a bulk of the fluid. This is, we are dealing in the convective. Therefore, this is bulk of fluid. We're trying to write a continuity equation, momentum equation, and also energy balance equation. But in order to do that, first we have to make a certain assumption. We assume it's a study two-dimensional, okay? just to find out, because the fluid is moving in this direction, but heat transfer valid in this direction, okay? The temperature change in this direction, velocity change in this direction, but also the temperature change along the x. Therefore, the fluid is coming here. The temperature here is, fluid has certain temperature, later on go to here another. Therefore, that's why we consider two-dimensional. Again, in order to be able to take advantage of some simplification, we assume is Newton fluid. Therefore, that means viscosity. And we assume the temperature is almost relatively in a range that we can assume the physical properties constant. And we assume is laminar flow, okay? Laminar flow, again, we don't want to deal with the vortex and fluctuation there. Therefore, we assume is this one. And therefore, our velocity is a two-dimension. We are going in this direction, velocity, and also as we move in this direction, the velocity change. Therefore, we have u and v. And we try to write three set of equation. Continuity equation, that's representing mass balance equation, momentum equation, and also energy equation. Therefore, we're trying to write this one. If you have any question, please do ask, okay? Therefore, we take this control volume. This is my control volume here. Is just show here is x direction and y direction. And we write the mass of the flow comes in equal the mass of flow going out. You have done it in fluid mechanics 65 times. Therefore, I'm just going to do it fast. Therefore, this is, we assume this is the area coming this direction, area here, and velocity is u. Therefore, it comes in and leaves in this direction, okay? Therefore, that's, we are writing, he's coming here and leaves in this direction. Therefore, in this direction, the velocity change from u to u plus du, okay? Therefore, that's coming in here and that leaves in this direction, okay? Therefore, that's coming, the velocity here is u, and this, the mass is coming here is rho ua, and the mass here is this times rho times a. Area remain constant, okay? This is this direction. And also we assume the fluid move up the direction because that velocity change. I hope if you have any question why these two velocity, please ask, okay? Therefore, here in this direction, flow is moving up direction. Therefore, we assume is also velocity mass is coming here is v rho times this area. This area is delta x times 1. And here it is delta x delta. Therefore, this is dy, the area come here, and here dx. And therefore, we write this in simple energy balance equation, mass balance equation, mass balance equation. And this is coming in x direction, coming here in y direction, and leaves in the x direction and y direction. If we simplify this equation here, remember here is this term that you have, the term you have here. We simplify, you will end up with a continuous equation that you have seen it in fluid mechanics. Therefore, this represents continuous equation, shows the variation of x to v in y direction, okay? That's, we call it by simple energy and mass balance equation that we wrote. Now we go to the second part. We write momentum equation, and you have done it many times again in fluid mechanics, okay? Therefore, here we can mention the differential equation form of equation motion in velocity layer are obtained by applying Newton's second law of motion, okay? It means Newton's second law of motion, I believe, I'm sure to understand. It means force is equal mass times acceleration. That's all he's saying, okay? Therefore, and we're trying to look at different type of the force acting on that control volume. Therefore, you have a fluid is in the motion, and there are a lot of force acts in that volume. And that's, for example, pressure, shear, and so on. Therefore, we're trying to take in consideration all the forces acting. As you know, here is mentioned, this is simply represent summation of the force on the acting in the system. Summation of the force is equal mass times acceleration. That's Newton's second law of motion, okay? I'm not talking about cooling, this is motion. Okay, this is represent here is second law here is mass times acceleration. We have to understand when the fluid is moving, what do we mean by acceleration? And net force of acting on that control volume. Therefore, you have a control volume, you have to identify what forces acting on that control volume, And then we try to find out what is representing x, acceleration, okay? Acceleration, mass, we know the mass of the fluid, that's dx dy times the other side. Considering this one, therefore we go back and mention this is force mass times acceleration in x direction is equal external forces that we had and body forces that we have, okay? What forces acting on the body and outside, okay? Therefore, here we might write down this is mass times acceleration. First, we define what is max. What is the mass here? The mass here is the dx dy. If you don't remember, that represented the mass. Dx times dy times the other length, okay? This is the volume, this is the mass of this volume. You have dx times dy and times the other length going the z direction, okay? But we consider two-dimensional, that the length is constant. Therefore, that's exactly representing the volume, dx times dy, and the other length we assume 1, okay? And time density. And now the question, what's acceleration? We define du is dux over, this is just a definition, the total differential equation, this is the meaning. And now we're trying to replace this one, trying to find what is acceleration, okay? Using this term that we have, d over dt, okay? Therefore, we take this one as a function of dt, okay? And therefore, we end up dx here, the acceleration, alpha x acceleration can simplify by this term, okay? This represents acceleration in terms of the velocity, okay? And then we move to write all the forces acting in the system. The forces acting in the system, as we mentioned, the fluid, we assume Newtonian. That's why we assume Newton, because we'll be able to define what is shear, okay? Therefore, here we have the force acting in the system. We have a shear in this, on this surface, and we have shear in this surface, and there are some external forces. Pressure drop is acting here, okay? There's a pressure causing a pressure drop, P and delta P here. Therefore, we write all the forces. Again, this is shear. We have to multiply by the area. Multiply by the area become force. Therefore, here we have d tau that we have here. We multiply by dx over down, and that's area. And this area acting in this one. And this equation will simplify to this term. This represents the shear because we have d here become the second derivative because we replace with tau and dp, and we have dx, and this is the area. Therefore, now we have be able to find the source of the pressure on the surfaces. Therefore, if we put all of the equation together, we end up in this equation that we end up. Therefore, this is your momentum equation. Simplify, this was, we mentioned, this acceleration represent. This is shear forces, and this is the pressure drop. We have dp over dx, that means the pressure changing as we move in the direction of x, okay? And here, shear on the surfaces that we have, okay? Therefore, we make some assumption to make it more, let's simplify this term, okay? If you look at here, we had also dp over dy, okay? But we are trying to ignore them because in the direction P, in this direction, the pressure drop compared to X is almost negligible. Therefore, we make a number of assumptions to end up with that equation that we end up here, okay? Again, every time we move in the equation, we're trying to find which term is dominating. We keep consider those terms are important, but we can ignore the other term that we mentioned here. Now we move to the second part. Again, this is something new for you because you have seen continuous equation, you have seen momentum equation, but now we are dealing with bulk of, we have this control volume, and we're trying to find what type of energy term involved. Again, the fluid is moving, okay? Therefore, we're trying to consider the general case, and then based on the general case, make a number of assumptions to simplify the equation. If you look at this, we mentioned the boundary condition, we have heat transfer going from the surface to the fluid. Therefore, you have some heat going in this direction. And also we assume because of fluid moving, probably there are some mass energy passed through the mass transfer, okay? As mass move, take some energy with itself, mc delta t. Again, we have a mass here in this direction, fluid has a certain velocity, and moving this direction, it has a certain temperature. When it got here, is another temperature. Therefore, we're trying to take in consideration all the possible mode of heat transfer. Motion of the fluid, conduction, convection, everything come together, okay? Therefore, if we start from that, therefore we write the energy balance. We mentioned energy comes in from here, and here is equal out this one and that one. And there is, we assume there is no storage capacity in that fluid, okay? Therefore, we assume the storage term is 0 here at this time, okay? Therefore, we write this term, there is no energy storage, there is no temperature as a function of the time. This is steady state flow, therefore this term is equal 0, okay? Therefore, we know if you look at the energy transfer, there is by heat, by work, as I mentioned, we consider general term, energy scenario, and also some energy moved by the mass. We try to find each of them separately, take into consideration when we write for this case that you have, okay? Therefore, we can write in this format, okay? We can write energy comes in, energy comes in, energy comes in, energy comes in, is equal energy out, 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 out. Therefore, in by heat, by work, and by mass. All of them we're trying to consider, okay? Later on, probably we can simplify the equation, okay? But let's look at the whole scenario. As I mentioned, we are talking energy, potential energy, energy, motion, velocity to power 2, all of them we take in consideration, okay? Again, energy is, therefore, energy interaction in all direction can be combined in one equation. Therefore, we're talking summation of energy. Therefore, for us at this moment, the energy, all of them, there is no direction vector. Therefore, we all of them consider energy to this control volume equal to 0. Look here on the, as I mentioned here, by heat, here, by work, by mass, okay? Let's look at by heat. By heat, it means could be conduction, okay? Therefore, energy comes in by conduction to this fluid, and energy leaves by conduction. Therefore, as we did it for solid, we mentioned Qx represent conduction comes in, and here conduction leaves, okay? And that's the term, the difference between this term and this term, this cancel out, and this become the result of this one. This d over dx is this one, Qx, it means Fourier equation. Therefore, this represents energy conduction in direction of x, okay? We assume at this moment, we didn't make any assumption. We assume the velocity, something, conduction is as important. Therefore, we consider the conduction term here, okay? That's what. Probably in the future, you mentioned, well, that the velocity moves so fast, I can ignore the conduction. That again, we can consider that one. By mass, okay? When we were talking about mass, again, remember static dynamic, we have enthalpy, even thermodynamic, we have kinetic, and we have potential energy. Therefore, this is the energy carried by the mass, okay? Therefore, we have to consider all of them, enthalpy Cp delta T, velocity in the x direction, y direction, and also moving, if there's a change in the height, there probably is a change. Therefore, you're familiar in the static dynamic or fluid mechanics, okay? Therefore, we write the energy comes in and energy leaves again. Again, the mass is coming, entering the system in x direction and leaving a different, okay? Therefore, we put the term and this term disappear, and we look at this part, okay? Because this is minus this one, okay? In minus out, okay? In minus out, this is the variation and the length of the delta x. There's a change of energy of the mass and that term, okay? Therefore, we can write it down and this term, and this is Cp delta, this is energy, and this is the mass of the fluid, and therefore we end up with this term, okay? We end up with this term that we consider, variation of the temperature and variation of the velocity. That part come from this term, and that part come from this term. For potential, we ignore it, okay? Emission is almost the same level. Therefore, we write all those equations again. This is simplify with this equation. And we have this continuity equation that we have it here, and we replace that one. Now, the other one is by, again, we mentioned by conduction, by this heat and so on. Therefore, we end up with this equation. The work done by force is determined by multiplying the force by the velocity in the direction of the force and volume. Again, velocity because variation we consider by electric acceleration, okay? The work needs to be considered only in the presence of significant gravitational, electrical, and so on. Therefore, when you're looking at what forces acting on the system, we have to look at it in case by case. Is it magnetic, if it's electronic, and so on, okay? Therefore, again, we make an assumption as we go through the system, okay? Again, the work is done by the pressure is already accounted. If enthalpy, we also consider it, and so on. We also consider the stress, shear, and also with the pressure and so on. We consider all the forces. Therefore, we consider all of them. Look at here that we have, let my screen become clear. Therefore, we end up with this equation that you have, okay? And these are mentioned by conduction. We mentioned repeat, this point comes in, this going out. Therefore, if we summarize all the equation that we have, again, we go one by one. If we assume there is only dealing with fluid, that viscous force is not contributing a lot. Therefore, the equation that we have is the one we had before. This shows variation of the energy, that we call it convective term, and this is a conductive term. Therefore, we wrote only for one dimension, but we wrote second dimension, this conduction term appear here, okay? Therefore, if you look at here, this shows velocity, we can add x direction and variation of the temperature, and also we have some variation of the temperature in the y direction. Again, case by case, we can simplify. For example, in some cases, I assume this velocity is negligible, I can cancel this term. I can assume the conduction in x direction is almost constant, I can ignore this one. Therefore, this is a sort of general equation, but still we make some assumption when we wrote the equation. For example, when we look at external force, shear, we did not consider this one. But with viscous shear are not negligible. If really the shear stress is really dominating and viscosity is very high, there is another term that we have it as a separate term here. Let me go to the term, if I have it here, my slide. But unfortunately, no, I don't have it my slide. But there are some term that was referring to the viscosity, we ignore it. Therefore, this term, you can see it in your textbook. There's another term that also shows the effect of the viscosity component, okay? Therefore, these are, we can see here is the term that we are referring to it, okay? This is the phi, okay? This term comes because of the viscosity term, because of the shear stress term. But in some fluid, when dealing with the air, we can ignore this term and only consider this equation. And this term represents the convective phenomena, and this represents the conduction in the x and y direction, okay? Therefore, this is the general equation that we have. Again, this is just, I don't want you, I'm not going to ask you to solve it, but at least to know how this equation end up like here. We wrote a simple continuity equation, momentum equation, and force energy balance equation. The reason why we need the continuity equation that we be able to find a relationship between these two velocity. Replace them here, okay? In order to do that, we have to solve continuity equation and momentum equation to be able to relate these two velocity together, okay? And now we have the temperature, it's become only as a function of temperature, and here is the second order we have to solve it, okay? But if you also consider, also the shear force, your equation become more complicated. You have x, another term here, okay? And that's okay. But that's not, as I mentioned, just to identify the terminology here. Which term represent what? Conduction x direction, convection y direction, and here is the convective term in the x direction and y direction, okay? Now, if you look at here, this is the problem we are trying to solve. And again, this is a very, very, very simple case. Very, very simple case, because we assume it's steady, we assume it's incompressible, and we assume it's laminar, because we can define the velocity as u, okay? And here we're trying to solve for this scenario, that the velocity in x equals 0 and y equals 0. Right here, the velocity here, u and v velocity are 0, and the temperature, yes. Again, this is we obtain it, this is we obtain it, and this equation. Therefore, we have to solve these three equations simultaneously, because from these two, we can calculate the velocity, and we can replace it here in the velocity if we calculate the temperature. This is a very complicated case. It's not easy, I'm telling you, but again, the idea is not trying to solve this equation, trying to understand the terminology, which term representing what, okay? And if we go later on, we can take more courses to find mathematics part of it. Therefore, based on this problem that we have, look at here, one boundary condition, and here two boundary condition, okay? Therefore, we end up with this boundary condition. At x equals 0, at the beginning of the plate, right here, the beginning of the plate, we assume the velocity, the temperature is this, and velocity here is undisturbed. Therefore, that's on my boundary condition that I have, okay? That's the terminology that I have here. At y equals 0, it means at the surface of the plate, at any point, the velocity is 0, okay? At any point, the velocity is 0 and temperature Ts. And that's exactly representing here. At any point in x, because we assume it's viscosity phenomena, therefore the velocity is 0, u and v, both in x direction and y direction is equal to 0, and the temperature is Ts, okay? And then we come here as y equal infinity. It means above the dimension infinity, it means over past the boundary layer, the velocity remain constant and temperature is constant. Again, if you would like to understand it, here is above here, this is my boundary layer that I have here. Therefore, above here, the velocity remain intact and the temperature not intact. Okay, T infinity, okay? That's the meaning here. The question here is the thickness of the boundary layer increasing slowly. We have to be able to find a way to calculate this thickness as a function of x, okay? Therefore, that's the question here is what I would like you, I don't want to memorize it. I don't want you yet to solve it. Just understand how you obtain this equation, just for your own information, for your future, that you be able to analyze the result. Because again, as an engineer, you have to, at the end, you have to have a judgment if the answer you got makes sense or not, okay? Now, when fluid property is assumed to be constant, again, we are trying to solve this differential equation. Look at here, I have viscosity. Of course, it's a kinematic viscosity. It means viscosity divided by density. And I have here also thermal diffusivity. Again, is rho, Cp, and K. Therefore, these are, again, we have to make an assumption. We are trying to solve all of them assumed to be constant. They are not as a function of x. They are not as a function of the temperature, okay? The two equations can be solved separately, and we can find these two velocity, okay? That's the first two equations. And then we replace these two. What we are saying here is we can solve this one independently because they are not a function of the t. We assuming this constant and so on, we can solve it based on the boundary condition that we have. And then when we find an expression for u, an expression for v here, we can replace it here and calculate the temperature. That's the way they will do it. Knowing this, the temperature becomes the only unknown temperature in the last equation, okay? Therefore, please try to understand the equation. You don't need to memorize it. You don't need to solve it. Just understand. And based on the boundary condition that we're trying to solve, therefore, the solution we find at the end is based on this boundary condition, okay? If the velocity is not v is changing, that equation does not be applied. Therefore, we make assume the velocity at x equals 0 is constant. Now, going back again, I'm sorry, again, I will go back. In heat transfer in fluid mechanics, we're trying we always trying to solve the differential equation, and sometimes we use the analogy. What do I mean by analogy? If I have another equation like this in any field, let's say in fluid mechanics or something like that, if I have the solution for that scenario, I will use the analogy to find the solution for here. The same thing we do it in heat transfer, mass, and fluid momentum equation. Sometimes I find, for example, there's a similarity between these two equations. Look at the similarity here is. Therefore, there is the form almost the same, okay? Therefore, if I can find a solution for this one, probably I can apply to this equation. Probably, okay, I'm not saying, I'm not sure, okay? These are, we use the analogy, we use it. And we use it extensively in heat transfer and mass transfer, okay? Mass transfer, we're talking about, for example, moisture transmission to the wall and so on, okay? Therefore, here it's mentioned here is the continuity and momentum equation are solved by transforming the two partial differential equation into a singular ordinary equation by introducing a new independent variable, similarity variable. The same thing with change of variable, okay? The argument, the non-dimensional velocity profile, this should remain unchanged when plotted against this one. Therefore, if I use non-dimensionalized form, the same thing that we did in the conduction, okay? If I find a solution, the solution is not anymore a function of a specific temperature. The solution can be applied to any range of the temperature. Therefore, we non-dimensionalize that similarity here, and we're trying to find a general format. This has no dimension and has no dimension, okay? Therefore, we are trying to do that. The same thing for the thickness, okay? They're trying to come with another terminology, okay? They do it this one. Thickness, the thickness of the boundary layer is proportional to this one. Therefore, we're trying to use the similarity to be able to solve the differential equation, okay? From here is pure differential equation mathematics. Please stay awake. Therefore, we're trying to find a way to define the stream function, that the stream function represents the two velocity, and they're trying to use the change of variable and so on, so on. Again, this the long procedure. You can read it in your textbook. Therefore, they end up to solve this equation defined here. Therefore, now you have this form of equation, which is a third order nonlinear differential equation. Therefore, the system of two partial equations transfer into a single ordinary differential equation, okay? Use of the similarity, okay? Therefore, they integrate these two equations together, find this one. And we're trying to solve this differential equation that we have here, this differential equation, okay? And then done as part of the numerical and so on, and trying to find what is f, what is this function, and so on, to be able to solve it, okay? This is the equation has been, the result has been shown here. We define what is n, what is f, and so on. Again, this is just for your information. After solving this one, substituting this and delta is, they were able to find an expression to find the thickness of the boundary layer. And the thickness of the boundary layer can be defined at this one. Look at here is 4.9, thickness, velocity, and so on, okay? Viscosity and so on. Therefore, that we change it to this, the form that we have here is. The thickness is 4.9, this Reynolds number. Again, look at here, it shows the thickness that is changing as a function of length of the plate. As we go further, this number will change. As we saw before, also the Reynolds number will change, because Reynolds number, the characteristic length is the length of the plate. Therefore, here it shows, and now we have an expression, and this expression that you can calculate the thickness of the velocity. This represents the velocity, okay? The velocity bond. Because we have also the thickness for the thermal temperature. This is represented for velocity, okay? Therefore, that's now one expression that you need to find here is interesting here, this one. Therefore, now you have an expression that you can calculate the thickness of the boundary point at any point. I'm not going to this part because this is fluid mechanic. And this one, I'm not interested in this part. And now we solved, again, going back to solve this part of defining tau, and they find the tau based on similarity. They did it find there's a constant number here, a constant number, velocity, and again, this represents a Reynolds number here. Therefore, now you can calculate shear as a function of velocity at every point in the plate. As you move them to plate, you can calculate shear. Remember this number here again. They use again, they can calculate friction factor. Now you have an expression that you can calculate the friction factor here, okay? And then we go solving this for velocity. We go to the second part, let's do the same thing for the energy. Therefore, so far we were able, by using the first two equations, integrate them together using similar variable, solving this non-dimensional term, finding this equation. They were able to solve it numerically, a combination numerically and analytically, to find that expression, to be able to calculate the thickness of the boundary layer for velocity, and calculate an expression that you can calculate shear force around any time, okay? Now we can go to the second part. Now we have an expression to this one. We go to the third equation, and we're trying to define another dimensionless number, the similar that we did it in chapter 5, and the equation end up this format here again. You have a V, and again we change the velocity. Now using non-dimensional term that we have, we end up that equation. Again, this equation representing a combined effect of the velocity and the temperature. Again, the boundary condition that you have at beginning the velocity, the temperature is equal to T infinity, based on the way it was defined. The temperature here is at the x equals 0 is T infinity. Therefore, this is the T infinity, this one. And then you have also T infinity at x equals infinity that you can define. By solving here, they will end up to find this term, okay? Remember here, let me go step by step again, behavior. Prandtl number for 1, this equation reduces to 649, okay? Theta replaced by this one. And we have a net for the case as Prandtl number because they're trying to, let me go back to here to see it. Yes, one equation, 649. And we do it here. Okay. And for non-dimensional temperature gradient, they have been able to find an expression to calculate theta here and fit, and this equal this term, okay? Therefore now the same way, again, we're trying to find, to calculate this, is going to look at here is the temperature as a function of non-dimensional length, okay? Therefore we solve this one, we end up to find this expression, okay? They go step by step, and at the end you find now you have been able to define the terminology based on your Nusselt number. Again, let me go one more step back here. Theta, and if you remember, is defined as this one. Okay, therefore this is the temperature. This is constant, this is constant, this is constant. The only unknown here, this term, okay? When they find an expression for theta, at the end, they can replace it by this terminology here, okay? Again, let me go back one more step to just remind you this did not come from Moon, that we define this terminology based on the term that we have. And N, this new define this terminology, okay? This is the dimensionless number, okay? This is a dimensionless number. Therefore, the temperature, dimensionless, and this is dimensionless thickness that we have here, okay? Therefore, here, when they define this terminology here, this is dimensionless temperature, this is dimensionless length, thickness, okay? They have been able to find, if we find this term, this derivative dimensionless equals 0, this is the Prandtl number, okay? Therefore, this we able to calculate here and then define the temperature profile. This is this one, okay? This is the terminology, the term dimensionless temperature. If you find that one at y equals 0, this is exactly the temperature profile. And the temperature profile at that time is represented by this term, okay? Look at here, you have a number, constant number. That represents the characteristic of the fluid to come bearing. And here is the velocity, and this is the temperature. Therefore, now we can define H equal Q by conduction divided by convection here. This time, this equal this. In order to calculate here, this conduction, as you remember, we mentioned we can assume the temperature profile in the thickness of the boundary layer is almost by conduction because we assume this motionless. Therefore, if we can find the profile of the temperature in that boundary layer at y equals 0, we can calculate this value. Now we have an expression that we calculate from here. Therefore, now we were able to find the heat transfer coefficient at a given point. Remember, this expression gives you the heat transfer at a specific point is equal to this one. And if you put them together, this becomes Prandtl number, and this can be defined as a Reynolds number. Okay, a Reynolds number. This is a characteristic length, the velocity, and the kinematic viscosity. Therefore, this will end up this one. Okay, this is your Reynolds number. And here, Prandtl number. So, therefore, we have been able to find a way to calculate the heat transfer coefficient. Again, this is the solution. As we mentioned here, we have two different forms. This is the solution for the case we have Prandtl number bigger than 0.6. For the other case, we find another solution. Therefore, now we have been able, again, the idea is not you solve the differential equation to find out how this expression obtained. We were able to solve the differential equation, find the temperature profile, and temperature profile given by this expression. Then we came back to what we defined at the beginning. The heat transfer at the boundary layer is, we can assume, is by conduction through the fluid, okay? Therefore, if I be able to define the temperature profile, I can easily calculate this value. And that we calculate the temperature profile here, we have expression, and that was the definition of heat transfer coefficient. We end up here, we put them together again, we give you a non-dimensional term. Non-dimensional term is the ratio of heat transfer by convective to the conduction. Now you have an expression for any scenario that you have a heat flow over a plate, you can calculate Nusselt number. But there is two conditions. This expression can be applied for case of Prandtl number is more than 0.6. And also we made one assumption. We assume the flow is laminar. Therefore, keep in mind, this expression gives you the heat transfer coefficient at the given point, X here, at the given point, it gives you at 0.6 meter, 60 centimeter. But if the flow is laminar and the Prandtl number like this, therefore we can be able to calculate this one. And also from there, based on the relation that we have here, we can also calculate the thickness of the Prandtl number, the thickness of the boundary layer. Look at here, we have an expression earlier. We show you an expression that you have an expression that you can calculate the thickness of the boundary layer for velocity. Boundary layer for velocity. And you can, from here, if you know the top of the fluid that you have, you can calculate the thickness for temperature. For a scenario, the Prandtl number is equal to 1. The thickness of the velocity for temperature is the same as thickness of the velocity for the velocity, okay? Thickness of the boundary for velocity is the same as thickness of the temperature profile, okay? Therefore, now we have at least three equations that we can calculate the thickness of the velocity profile, the thickness of the temperature profile, and also for the case of that we have dealing with a laminar flow and Prandtl number is more than this, we can calculate also the heat transfer coefficient. Any question? Any question? Are you awake?
Yes, sir.
Good. Therefore, again, this is not the question trying to solve this differential equation. That's nobody's going to ask you. The question to know how we actually obtain that one. Therefore, we took a control volume, we wrote a mass balance equation, we wrote a momentum equation, and the energy balance equation. the question you'll be able to identify the term that we consider. Why we ignore some of them? Why? These are based on assumption that we made. Okay. Again, nobody going to ask you to solve this differential equation because it takes another 2-3 months for you. But how we started and what we end up here, and that's we use again advanced mathematics. You're trying to use 9-dimensional to find a solution to that one. When you find that solution to thermal velocity, you can apply it for the temperature and so on. That was the analogy that we are using. Let's see how we can apply it. Again, we come back every so often to look at here. Look at here. It's problem from chapter 6 edition. Try to understand the problem. It's not the solution important. Water at 20 degrees is flowing over velocity about 0.5 meters per second between two parallel plates. The distance between two parallel plates is 1 centimeter. Determine the distance from the entrance from x equals 0, at which the velocity profile and thermal boundary layer meet, where there is to meet. How are we going to solve? I do not know how it's done. Therefore, we have two parallel plates, and the flow is passing between these two. Describe to me the phenomena. We have the solution here for one flow, okay? I have only one plate, and the flow slowly move in this direction. Therefore, the velocity here is 0, slowly the velocity is increasing and so here. Now, in this case, he's saying we have two. We have another plate here. We have another plate here, and the flow is coming here. What will happen?
Sorry?
Yes, sir.
They should meet when both velocity and temperature are equal.
I do not know it's equal.
The other? Is that
say it again. Say it again.
Can we consider only one plate first, and then consider the other plate, and the layers meet when they're both equal, if they start at the same place?
Very good. You started very good.
They have the same roughness, I guess.
Pardon me?
And if they have the same roughness as well.
No, the same plate. The plate are identical.
Okay.
We try. The plate are identical, and they are 1 centimeter from each other. Okay. Now, what will happen? Therefore, if you look at separately, the bottom one, the velocity profile will go like this. If I go a little bit further, let me go. I really missed the blackboard, my friend. Here, look at here. Jesus Christ. What happened? Here. If you assume only one plate, okay, my friend? If you look at here, this boundary layer, it grow, it can go all the way to here. Now assume there's another plate on the top. What will happen? You have a boundary layer also coming, going like this. Am I correct?
Yes, sir.
Therefore, you have a plate right here. The velocity profile for the lower boundary is like this. And if you have another plate on the top, the distance between them is, let's say, 1 centimeter. Up there also starts, if you look at separately, you have the velocity profile is also growing like this. And reach at a certain distance, You have this velocity pushing up, and the up velocity is pushing down, right? Where should be in that point on the y direction? They have
half a centimeter.
half of middle of the plate, right?
Yes.
That's a half. Okay. Therefore, that's the physics of it that you should understand. Yes, this boundary layer is growing slowly, 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 and the other one is growing up here. But since they are identical plate, the velocity profile have the same force to each other. Therefore, they agree to meet each other at the center. And then after center, this one remain constant and that one remain constant. Therefore, eventually they meet each other at the center of the pipe. Is this clear?
Yes.
Those of you quiet, is it clear or not?
Yes.
Good. Now, therefore, they meet each other at the center of the plate. Let's go back. Where should be that one now? How far is from the pipe? Okay. Therefore, here is two polar plate. Therefore, the velocity in the bottom plate is start to grow. On the top one is start to grow. And these two plates are 1 centimeter apart. Therefore, they are forced to meet each other at the center. At the center, okay? The question that he's not asking you where it's going to meet. It's going to, the distance from the beginning of the pipe. He wants to know the x, how far it will take the velocity profile reach at the center, how far it takes for the temperature profile meet at the center. How can we calculate that part? Read the problem one more time. Okay, this is the question here. We are trying to look at here, we make isothermal condition exists between the plate, therefore, and velocity profile I assume constant. This is assume, okay? He's asking you the distance. He wants from the beginning x equals 0, how long it takes the velocity profile reach at the center, how far it takes for the temperature profile meet the center, because we agree, since they are symmetric, they have to meet each other at the center. That's why we can, when we are dealing with the pipe, we assume the velocity is maximum at the center, okay? Because pipe is symmetric, okay? Now, could you answer to this question now? Now, let's go back what we learned. We learned we have an expression that we can calculate the velocity profile. Therefore, this represents the thickness. I know it meet at the center. Therefore, I know this is 0.5 centimeter. Therefore, I know 0.5 centimeter, but I do not know the x. Therefore, replacing this equation, I'm trying to find where, at which point they meet each other. Okay? Is it clear? Therefore, now we have an expression. We can calculate the thickness of the boundary layer for velocity. And we meant the question here at which point they meet each other. We agree they meet each other at the center of the plate.
So
0.5. That's right. Therefore, we can go back and start to do it this one. Now, to do that, we need to calculate the Reynolds number. Reynolds number, we need to know the characteristic of the fluid. Therefore, we need to know the physical property. Therefore, we have to go table A.9, and table A.9 give us the physical property of the water. Therefore, we go open your textbook, table A9, and I believe you mentioned the density is this one, viscosity here, and the Prandtl number is this one. You do the rest, please. Therefore, we are talking about the plate. Therefore, the characteristic length is equal to x. We have the physical property, and we're trying to calculate the Reynolds number. Therefore, the length is unknown again in this Reynolds number. Therefore, here is the kinetic viscosity at 20 degrees. This is, again, because the equation is giving you the kinematic viscosity, and kinematic viscosity is given directly in table, but also you can find mu viscosity divided by, call it kinematic viscosity, and that's the value. And this is the problem with helium. If you look at this plate, the velocity profile, it grows. If this is not there, this will go up right here. As x increases, this velocity profile increases like this. But if I ignore this one and look at the up one, this velocity profile also increases. But since this is symmetric, this is the same material, the same roughness, the same temperature, the same thing. Therefore, this both are developing simultaneously together, okay? And they reach at the point, this velocity would like to go here, this velocity want to here. But since the forces are equal, they agree together to go like this, okay? Therefore, from here, the velocity profile remain constant. And that's exactly, we look at the pipe, we mentioned the maximum velocity take place at the center. This is the physics behind. That's why the reason behind, because the pipe is similar like this, okay? Therefore, now we have this one. We know they meet each other at the center, 0.5. The question here is, what is the distance from here to here? I'm trying to look at here. And we have an expression that gives us the thickness as a function of the length. And that's exactly that one here, okay? This is we discuss. Both velocity and temperature profile meet at the center between the two plates. And at that place, the thickness of this and this is equal to 1. It doesn't mean both of them will be the same point. No, they will not be the same. But eventually, the temperature and this one meets probably the velocity here, the temperature here. We are trying to find this thickness. Now, based on your understanding, does the velocity meet faster or the temperature? Does the velocity profile meet sooner or the temperature? Which one and why? The answer is easy. The answer is right here. Here again, please pay attention. You mentioned the difference, the ratio of this thickness, velocity thickness to temperature thickness is Prandtl number 213. What was the Prandtl of the water? We saw it in the table. I believe this tell you why. This divided by this Prandtl number was 2 something. Therefore, this will be longer than temperature, okay? Therefore, you look at here. Pay attention, ask me a question. No, it's not face and face, therefore, please ask me. Therefore, now we have an expression that this is, again, please remember, this is for laminar, for laminar, for laminar. It's not for turbine. We were able to find an expression to give us the thickness of the velocity as a function of the x. You can write in this format, or we can write it in the format of Reynolds number, okay? That's why in the other format, we have an x here. Here, we don't have an x, okay? Because velocity times x, that's why we have here. Therefore, here we have an expression. You have the velocity, you have the kinematic viscosity, and the distance. This is unknown. We are trying to see where the velocity reaches center. But we know this is 0.5. If you substitute there, you find it takes almost that length for the velocity to reach at the center. Therefore, after 0.5, 6 here, the velocity profile meet each other. Now we would like to go and calculate for the temperature, okay? Could you please do it? Read the problem. Please read the problem. For the God's sake, do not memorize it. Read the problem and ask me any question that you may have. The question was, calculate the distance from the entrance where the velocity profile and wonder, okay? For here, we mentioned the velocity profile right here at the center. We're trying to find the temperature profile, and then after that, these two, both of them moving together, okay? Write it down. If you have any question, please ask. After this, we have no much mathematics, okay? This is good news. Now we go back here. Now we find after 5 point this, you can use this expression here, or we can go back and use the information that what they have the thickness of between bundle layer, okay? And here the expression that you have for the temperature bundle layer, okay? Again, the same equation, but here we have this Prandtl number. And we have we obtain this Prandtl number again, where it comes from. It comes from the textbook, and the Prandtl number is 7. Okay, 7 right here. This number here. I'm sorry again, but I'm going back and forth here. Therefore, you have this expression. You have the same velocity. You have the Prandtl number. You have kinematic viscosity. You have 0.5 centimeter. The unknown here is the temperature. The unknown here is the distance from the beginning. Therefore, this is the thickness of the temperature profile, okay? Therefore, you come back here, you put the number here, and you can see the temperature profile will develop much later, 3 times later, okay? That was 0.5, here is 1.8. Therefore, at that point, the velocity profile and temperature profile, they go together, okay? Before that, temperature velocity also was already developed at the center, where it takes almost 1.9 meter, 190 centimeter, but the velocity slowly to grow to get to the center. Okay? Any question, please? Therefore, please try to understand the physics behind it, because that will help you a lot in trying to solve the problem in the future, okay?
Sir, I have a question.
Yes, sir.
At the beginning, we know the velocity profile of the fluid for one plate. I'm just not seeing how are 2 plates meeting together at the center. Yeah. Okay.
Look at here.
Yeah.
Ignore this part, the top one. And let me go back again to those one that give you wilder idea. Look at this one. One plate. Look at here, this velocity here is slowly is coming up, okay? It means here is changing, slowly, and this is continuing growing, okay? So this is go, as if this plate goes to infinity, this continuously grow, okay? It is nothing there is to control this one. Put another plate on the top, right here, okay? Put on top. The same thing will happen for this plate that you have here. Okay, if there is this does not exist, if does one does not exist, and you have a plate here, and air is coming here, the velocity profile grows like this.
Okay,
right?
is that true? Like at the point they have in contact, the velocity is the same?
The velocity is the same. It means if you look at here, the velocity here, it represents when they meet, the velocity at this point here is the maximum. Because here is velocity slowly increasing. And if you have another plate in the top, velocity slowly is increasing. Therefore, this velocity become maximum.
Okay, yeah.
That's exactly happened in the pipe. In the pipe, if you look at the velocity in the pipe, we mentioned at the center is the maximum. And because of this phenomena, because here is the slowly velocity is increasing, because here is still under control of influence of the viscosity. And after this line, the velocity is not influenced by the viscosity. Therefore, the velocity here is the same velocity as here. But in here, in this layer, the velocity is less than this velocity. This is the velocity maximum, okay?
Okay, I see. Thank you.
No problem, sir. Okay, ladies and gentlemen, please ask, because I do not see your face, therefore it's very difficult for me to understand.
Can you go back to the same page? No, not up. The last page of the example.
Okay.
I have time to
okay, this is here. I will the left.
After for the layer of T. Yes, perfect. Thank you.
Ask, please, the rest, ask question. I only hear 3-4 voices. You're 51 of you. I do not know the other one. Watching Netflix, Apple, Google, or listening to me. Now, my answer, is it correct or wrong?
Shouldn't be the opposite?
No. Why? Just go back and look at that. You have the thickness.
Right.
No, because we have a ratio of velocity.
Yeah, no, it's fine.
Now, tell me, my answer is correct or not? And 90% of the time, my answer is wrong. How can I make sure this is correct?
Can we use the PR?
No. The only thing here is we made an assumption. When we use this equation, we made an assumption. What was the assumption?
The flow is laminar.
Excellent. Therefore, I have to go back and calculate if my assumption is correct. Therefore, what about the assumption? Because we assume it's laminar, and based on the laminar, I start to use this equation or the previous one. Therefore, I have to go back and verify if this assumption was correct or wrong. If it's turbulent, that's not correct at all, okay? Therefore, we go back and calculate my Reynolds number. Therefore, here, let's say for velocity at least, I look at here, because I'm dealing with this one, and I look at, and I calculate my laminar velocity, it was 0.5. The X, I'm trying to see at X equal 0.516, my velocity profile is laminar or turbulent. Here, the number, and this is the kinematic viscosity, and fine, here is. Now, ladies and gentlemen, is this laminar or turbulent?
It's laminar.
Why? It's more than 2000. You're right. You're right. You're talking about flow over a plate. And if we mentioned before, you're right, madam, you mentioned before that the Reynolds number is less than 500,000. The flow is laminar. If it's more than 500,000, it's become transition and turbulent. Therefore, we are talking about flow over a flat plate. Therefore, here it is laminar because the Reynolds number here is less than 500,000. Therefore, 2000 is only for flow inside the pipe. But we are talking about the flat, okay? Now we can come back, and because we discussed it later on, if how our assumption was made here, because we look at again the flow over a flat plate. Over a flat plate, we consider independent before this length, flow were independent from the lower plate and upper plate. And after that, become measure, okay? Therefore, now we start to have at least some idea how we are going to make a calculation about the heat transfer coefficient. Let's go back to the next problem and try to see if there is a way, because now I can have some idea what the velocity thickness, temperature thickness, but my goal objective in heat transfer here is trying to calculate the heat transfer coefficient. Let's look at this plate and try to read it and try to understand, because we are going back to fundamental that we discussed, the basic concept that in the boundary layer, we can assume the heat transfer is by conduction, okay? Read this one and to see how we can use that assumption. We have a metal plate here, and we have some air going up there at a given temperature and velocity. It means heat transfer coefficient, and we have hot steam down here, okay? The metal plate is being cooled by air right here, and mention the conductivity of air is given. At the upper surface wall and the lower surface is a uniform heat flux of 1000 watts. Therefore, here is the steam comes and provide a uniform heat flux. Therefore, we're not dealing with convection here. We have a uniform heat flux going to the plate. Determine the temperature gradient in the air. I want to find out what is the temperature gradient here at the upper surface. I want to find the temperature profile, because if I find the temperature profile, I can easily calculate the heat transfer coefficient. How can I solve this problem? Therefore, I'm trying to find an expression for the temperature as a function of the y, and right here. Any idea? But again, look at here, we are dealing with a steady state scenario, okay? Steady state scenario. It means that whatever heat flux comes from here goes to the plate and goes to the air. Here is cooled down. Here we are providing 1000 watts per square meter. Here we're talking about the solid material, and then goes to here, okay? That's a steady state scenario, okay? Therefore, look at here. Every time we would like to solve a problem, we have to put the boundary. The solution, our solution is only valid for such scenario. We assume a steady state condition. The thermal conductivity of the plate is constant. It's not a function of the temperature. Convective transfer is constant because we are assuming it's a steady state scenario. And heat transfer is only one dimensional. It means the temperature of the plate here is the same as the temperature here. The temperature of the plate here is the same as it's one dimensional. It's not two dimensional. Okay? If the air is cooled, in reality, the plate probably the temperature will drop. I do not know. Okay? But we assume it's a constant heat flux. Okay? Therefore, we assume the temperature here is gone. Okay? The conduction solid is one dimensional, and non-slip conditions available. Again, we assume there's a velocity profile, there's viscosity will affect the velocity profile and eventually the temperature profile. Okay, these are some of the assumptions that we can make. Okay, probably you have some more in your mind. Okay, now, as I mentioned, steady state. What that means, heat by convection, heat flux to here is the same as here and the same as here. Okay, that's exactly what we do here. Therefore, here we assume, I don't know, these equations appear here. Therefore, we assume here is we assume this is conductivity of the plate, okay? Therefore, you know the heat flux coming here, but you do not know the temperature here. You do not know the temperature here. And by the only thing we know, this is the air is going to this direction, but this more. Therefore, I can write the conduction here is steam is coming, because steam here by convective is equal by conductive here, because as I mentioned, is a steady state scenario. Convective, conductive, convective, all of them are the same. And I can easily write this expression. But here I know how much this value it is, but let's look at here. Therefore, I know convective by heat transfer by steam, but it already gave us this value. It already gave us this value, okay? Is equal by convective here, okay? But here is in steam, it still is convective heat transfer, okay? It still is convective heat transfer. And the temperature getting in the head and the top can be calculated by this expression. Therefore, here we have the convective, this part, convective, this part. This value is known because give us the value. And now here is equal to convective this transfer here. But we mentioned, remember, that the boundary layer is the heat transfer by conduction. Therefore, I can calculate, mention this expression here. This expression here is equal to the conduction through the boundary layer. It is equal K of air times this one. Therefore, this is equal K of air times this one. Therefore, this one. By equating this equation, I can calculate the H of air. And H of air is explained right here. And this is the temperature profile that I have here. Therefore, if somehow I can calculate this value, I can easily calculate this one because this is unknown. This is unknown. Please, you continue trying to do the rest to see if my solution can help you. Try to read the problem, please. Try to read the problem, understand it, and then let's continue. Find out what is given and what is unknown and what you suggest to get that one, okay? That was my solution. I do not know if I'm correct or not. Read the problem. What we are trying to calculate, we would like to calculate the temperature profile here, the temperature gradient in the air, right here. I'm trying to calculate the temperature. I don't know if you can see it in this message. I do not know. He's asking me.
Just put remind me later.
No, I don't want. I mean, why interfere me? Okay. Therefore, what we did, we mentioned this is we have to try to find the temperature profile here. We know the temperature of the air after the boundary layer is to infinity, but I do not know the temperature here. What we did, we mentioned, let's look at here. The convection here equal to convection here is equal to conduction through here, okay? I'm not interested in conduction to solid. I'm interested in conduction in the boundary layer, okay? Therefore, this is, we wrote convective here, the value is known here, give us 1000. This is the heat transfer convective from the surface to the bulk. This is the temperature of the bulk. This infinity is after the thickness, okay? This is equal to the convection in the boundary layer is equal K dt over dy at y equals 0. And then by putting together, I end up this expression here. Therefore, here, as the temperature profile I'm interested to find out, this value right here is equal to this value. Therefore, I can easily replace it by this steam. Okay. Any question from here to here, please ask. Any question at any step, let me explain it to you, please. Therefore, now, as I mentioned, we know this value here. This is Ka, okay? Therefore, we were trying to calculate this profile. What should be the next step? Okay, let's go to the next step. Since we know this value, we know the K of R, it gives us the value of the temperature profile at the, here is equal this one. The temperature profile is 2,469 degree per minute, okay? Per meter, okay? Therefore, this is the slope of that line at that profile, okay? Therefore, this is the slope of the temperature at that point, okay? Therefore, here, this we calculate it and we obtain, and we can calculate the temperature gradient on the top surface. This is the value. If you would like to calculate the bottom plate, this is the bottom plate, okay? It gives us the value. Anyway, go back again, please read the problem one more time. Probably all the information is not given here. I should cut it and paste here. Read the problem and we continue. Try to understand. The solution is not important. Try to understand the concept behind it. How we define the convective heat transfer. What was the starting point? The starting point we mentioned here is the convective heat transfer is the heat transfer go from the plate to the bulk. This is T infinity. At the very close to the surface, to the boundary layer, the heat transfer is by convective heat transfer to the air, okay? Please read the problem one more time. Try to do it. We solve it again next time, okay? But first, try to really understand the concept behind it. The solution is not important. Do you have any question about the project? Do you have any question about the project? Do you have any comment about the tutorial? Somebody should answer in something.
Sorry, if we have an issue with our code, can we send it to the TA so she or can revise it?
They don't revise it. The question, they are not there to teach you to, but they can help you to tell you what is the problem, okay?
Yes.
You won't expect it because you see, look at your 75 of you, okay? We don't have time to sit down and go through one by one code, but you can raise question, what is the problem? They can give you a general solution. And again, this is, unfortunately, these days, we have not much contact. It's very difficult from your side point of view and from our side of point of view, okay? But we try our best to see what we can do for you.
Okay.
But again, these all of them, they're very familiar with the MATLAB, and they can probably give you some suggestion. But before sending to them, again, look at your equation to see if you're correct or not. If you have done correctly the first part, the second part is only just adding some term, and that it goes through the loop. Have you received your report for number 1?
Yes, she just sent it while we were in this class.
Oh, he's interrupting my class now. Okay. Therefore, look at your report, because I asked him to look at it and provide you, at least we met each other and we went through a few of them, and we tried to provide you some feedback. Read your feedback to see what part is, again, this is not an assignment, this is a project. You have to be able to explain it. Don't tell me my result temperature is this. Justify why the temperature that suddenly at 11 o'clock drop. Because
for the comments on the reports, like sometimes there's maybe code related issue, but like I quickly checked and the comments are more like on the format of the report and not
again,
not say like, oh, you have like, it's like if the code haven't been checked at all, because sometimes we have unexpected result, but at some point if we work and continue to work and like we must give you something, so sometimes we try to justify, but then there's no comments on that. So like, I don't know, like I'll contact the TA, but like, could it be possible for the second one to have some more like?
You see,
comments?
Corona, the idea is not to correct your code. The idea is the judgment.
Okay, but then if I lose marks because there is something code related,
Let me just explain
okay.
what that means. If you get the answer, the temperature in the room is 95. At least because we got some cases, the temperature was 250 degrees in the room. At least some of the one of the report we checked together, okay? Because I went to school and we sat down and we look at a few of them to just have a uniform, this one. And there is no explanation why the temperature is 200 degrees. Again, if you tell me, yes, the temperature should not be 250 degrees, and that is the reason probably a mistake in my code, that at least we can say, okay, he or she has a certain judgment. Because you're talking about your future. Your future, you get a job and use any code, and you get the wrong answer. You go to the court and you tell the judge, I got from the code, you are reliable because you have engineering judgment. And you have to be able to mention when went wrong, okay? And that's some of the thing we expect from you, because this is, if you look at course outline, this is part of accreditation. They are saying, does your student have judgment or not?
Okay, so if we have put a judgment that it is
Explain it.
clear that that was very unexpected and not normal,
Yeah,
and we've lost points for it, then what, like, what's going on? This is my question. It's more like, I totally understand that, yes, we must be able to analyze, and this is the point of the whole thing.
There is, if you look at it, I believe there's 4 points that we are answering. The communication, one part. Engineering, one part. And there is code part is another part, okay? Therefore, this is the part when we read, we would like to look at, again, this is not an assignment. This is the project to be able to explain it. This is my answer, and this is the way I'm going to solve the problem, and so on, okay? Again, we don't have time, and that's not part of our responsibility to go sit down in code and look at which line you made mistake. This is your responsibility. All of you guys have taken a course on MATLAB or C++, I don't know what was the course name, okay? Therefore, this is not part of that course. We are not going to teach you solve first order differential equation. This is part of your responsibility to know that. Based on that part, we're trying to understand also your scenario. Okay, again, we understand this is the social distancing. We cannot sit down and look at your program line by line. But again, you are 75 codes. How we can have time to go to all of them? We look at your answer. You're responsible mathematically, you're responsible for code, and so on. Therefore, we try and also understand your scenario. Any other question? Again, please, again, going back to the question you asked, please, if you have any question, you can ask the TA, just mention this is the problem I have, and do you have any suggestion? But do not expect that we can sit down and look at 75, 80 program line by line, trying to find what is your mistake. Yes, sir. I'm sorry.
Yeah, sorry. What will be the format of the midterm and the final exam? I am new to Concordia. What will be the format of the midterm and the final exam? Is it will be like an open book? Sorry, I'm new to the Concordia and I'm not familiar with the exams.
Okay, sir. You're going too fast. We are talking about the project. Who cares about the final anyway?
Or the midterm.
The midterm, okay. It's going, as I mentioned here, you can bring 4 pages of formula. And that's the reason, because we're trying to help you to focus, okay? As you read, as you go through the textbook, trying to find which equation that you really need to, because I'm trying to discourage you memorize them. You can bring 4 pages of the formula, okay? 1, 2, 3, 4, okay? And if there is something really needed, I will provide you. For example, the table, you do not need to write it down. If you need those table equation in the table, we provide you those table, okay? And the format is closed book, but you can bring 4 pages of a formula sheet. And what else, sir?
It will be on the call website?
Of course. Because it's going to be in code. That's right,
Excuse
sir.
me, Professor. So we
Yes,
are
sir.
going to write our formula sheets.
Yes.
Okay.
You want to do it? Do you want to do it for you?
No, it's okay. I'm just asking.
No, it's
I have another question concerning the project too.
just let me just finish. The reason I'm saying you, because you at least you're familiar with your own writing and you know where you put the information. Okay. And also, as I mentioned, if there is some equation is given in the table, you do not need to write those equations. I will provide you. Okay. Therefore, we are trying to make it easy for you that you write it your own handwriting and you know what it is, and then trying to use it fast. Okay.
Okay, so I will answer on a piece of paper and take photo of this paper and upload it, or how to work?
No. You write it. You bring it yourself. You don't.
No, I mean the answers.
The answer, I have no idea. I believe you have to upload it. You have to take a picture of that. This is. I'm going to get more information. I will try to send it. I believe you have taken some of you in summer course, or you are already familiar with that one. You're much familiar than me.
Sorry, it's first time for me.
Okay.
But there's different scenario. Like some teacher, they like give an exam, and then we have our own thing that then we have to upload. And then there's another way of like answering on the computer and having our formula sheet prepared like online. So like if you tell us to do like 4-page, do we need to memorize it, or like we must know in advance to prepare for that at least?
I will try to get that information for you because I do not know how the hell this call is working. Therefore, this will be done through university, and as they ask more information, I will provide you with information. But you can, as I mentioned, you can at this moment you can prepare your 4 pages of formula because your pages as we go through the term will change. Because for the midterm we have until end of chapter 5 or 6. I do not know what it is, and then you're adding more formula. But if there is some equation is given the form of the table in your textbook, because some of the equation in chapter 4 or 5 are given the form of table, and I will provide you as during the exam. But yes, you are right. We will provide you more information as we go ahead.
Okay, thank you.
Thank you.
There was one question about the project. So
It was me.
I'm sorry, I interrupted you. I'm sorry.
It's okay. So basically for project number 2, we have to write a new methodology, new intro, nothing from project 1, right? Or we have to like continue what was written and add the thermal storage.
No, you started. I mean, the question, this is absolutely independent from project number 1, okay? But because the equation will be different, but of course, some of the information will be the same. Therefore, this will be independent from the project number 1. Assume this new project and you have to write a project because he's going to mark this one separately, okay? Therefore, he doesn't remember 75 reports. But again, the information is not related. The only thing about the physical characteristic of the wall and so on, these are the common part. Just description of the project, but the solution will be different, the answer will be different, and so on and so on. Did I answer your question correctly, Sarah?
Yeah. But what I don't understand is that we still have all the components like conduction, convection, radiation. We just add the thermal storage. So why can't we just continue, let's say the introduction, we keep as it is, and we just add the thermal storage thing?
Sure. As I mentioned, again, probably I answered you. I mentioned is independent. You can take as much as information from your report 1, put in report 2.
Okay, cool.
As I mentioned, is independent. Okay, you take whatever information is in your project number 1 that needed for project number 2. That's fine.
Okay, perfect. Thank you.
Sure. Any other question? Okay. Have a nice evening. Please read this problem. Yes, dear.
I just said have a great day.
Oh, you too. Thank you very much. Appreciate it. Therefore, please read this problem from your textbook and we solve it in the next lecture, okay? All the best.
Thank you,
Bye.
sir.
Have a good day.
You too. All the best.